when we look up at the night sky, we have the feeling that it's quiet and peaceful, basically unchanging. In fact, we often talk about things being as constant as the stars. So, what would your reaction be if I were to say, if you could come back to this spot sometime in the distant future, the stars would look completely different? I don't just mean they'll have moved, I mean their whole appearance will have changed. Some will be a different colour, others will be much, much brighter. And one or two may even have flared up and then disappeared completely from view. Well, that is exactly what we do believe. Far from being peaceful, we think there's a tumult of activity going on up there. Stars are being born, are growing old, and are dying. Now, why should we believe that? Well, that's what this program's all about. The way in which scientists, astronomers, have collected together, sorted out, and then interpreted the bits of information which have led to that conclusion. And it's really a rather remarkable story. After all we've got to go on is the starlight itself, albeit observed through big telescopes like this one at the Royal Greenwich Observatory. But how does that help us find out about the behaviour of stars? What can we actually measure?
The first and most obvious thing to measure is the brightness of a star. And that needs a telescope to collect the light over a known area, the 36-inch diameter mirror, in the case of this telescope, and it needs a light detector. Photographic plate is a very convenient detector. By measuring the strengths of the images on a plate, properly and very carefully calibrated, the brightnesses of two stars can be compared. But, of course, just because one star looks brighter than another, it doesn't mean that that star is giving off more light, because the amount of light picked up by the telescope depends also on the distance of the star. For instance, look at these two stars here. This one looks brighter, it's a stronger image than this one. But it may be that this star is simply closer to the Earth and therefore looks brighter. But if the distance of the star is known, perhaps by using one of the methods which is described in the text, then the total amount of light leaving the surface of the star can be worked out, and that's what's called the absolute luminosity. Now, another difference, which has turned out to be extremely important to astronomers, is that stars have different colours. That's not obvious just looking up at the sky, because the ability of the eye to distinguish between different colours fades away in dim light. That's why it's difficult to see colours in moonlight. There are a few stars which are bright enough to see the difference in colour, but try looking at the night sky during these winter months, in particular at the constellation of Orion, the Hunter. There are two stars which are bright enough to show definite colours. Betelgeuse, at the top left of Orion, shows a definite reddish tinge, whilst Rigel, at the bottom right, is bluish. And of course, looking through a telescope, which collects much more light, then the difference in colours is even more striking. This is a blue star seen at high magnification through a large telescope. The star itself is just a point of light, but the Earth's atmosphere causes the twinkling and shimmering. And a red star, no mistaking the difference in colour here. But it's not good enough just to describe the colours. What an astronomer needs is a numerical measure of the colour of a star. And this is the instrument which does it, a spectrograph. Takes the light from the mirror, splits it into its component colours so that the spectrum of the star can be recorded. Well, now the light from one single star is much too dim to be able to see what's going on inside here. So let's instead look at the light from our nearest star, the Sun. The Solar Astronomy Laboratory at Oxford is designed to do just that. Sunlight is directed by a telescope down a fixed tube into the laboratory. And there it reaches a focus at the front end of their spectrograph to make a large image of the Sun.
Sunspots and all, you see. And some of the light passes through the entrance slits. From the other side of the slits, the light diverges to fall on a mirror, to be bent down in this direction to fall on a concave mirror. Now this has the effect of producing a parallel beam of light, which comes back to this unit here, which is the heart of the instrument, the diffraction grating. And what that does is it bends different colours through different angles. So from the diffraction grating, these different coloured parallel beams come down here to fall on this concave, second concave mirror, and from here the light is focused down by another plane mirror to produce a beautiful focused image of the spectrum here. And this is the spectrum of a star, in this case our sun. But it's all still a bit qualitative, because what we really want to know is how the intensity varies as a function of wavelength. And to do that, I've had to modify the Oxford equipment a bit more. I've introduced some bits and pieces of our own. This lens takes the spectrum and projects it to give a magnified spectrum on the chart recorder here. And this is a photosensitive detector which will pick up the light and feed the signal to the pen. Let me run the spectrum now. As the detector scans through the spectrum, the pen plots out the variation of intensity with wavelength. And I think you can see that it's peaking nicely in the green, about 500 nanometers, even without having corrected for such things as the atmospheric absorption. Now, although this whole system has been set up for sunlight, in principle it would be no different for dim starlight. We'd simply have to enclose the whole thing and go to sensitive photographic film or something. But when we do that, then we get, for instance, the spectrum of Betelgeuse looking like this. And the spectrum of Rigel like this, where I think you can see there's much more blue light. And when we convert these into their respective spectral curves, we see that Betelgeuse peaks at just over 800 nanometers in the infrared, whereas Rigel peaks in the ultraviolet, somewhat below 300 nanometers. Compare these with the sun's curve, peaking, as we've just seen, in the green at about 500 nanometers. Now, you remember from the main text that the further towards the blue the peak of the spectral curve occurs, then the hotter the surface temperature of the star. In fact, by measuring the position of the peaks, we can deduce that Rigel is at about 11,000 Kelvin, the Sun about 6,000 Kelvin, and Betelgeuse at 3,500 Kelvin or thereabouts.
So we have these two parameters, absolute luminosity and temperature. When accurate measurements of those two parameters first became available in the early years of this century, it opened a new phase in astrophysics, because there's a pattern in those data. A pattern that was discovered by two astronomers independently. Einar Hertzsprung, who was Danish, a self-taught chemical engineer, photographer, became fascinated with astronomy, and Henry Norris Russell, an American. He was going to be an astronomer right from the beginning. He studied and worked in Cambridge and Princeton in the United States. The starting point for both of them was to plot luminosity against temperature. Now, in the beginning, they only had a few dozen well-measured stars to work with. Nowadays, of course, there's vastly more data available, and today it's stored, like most data, on a computer. The Starlink computer system links the universities of London, Cambridge, Manchester, Edinburgh, and the Rutherford and Appleton laboratory with this terminal at the Royal Greenwich Observatory in Herstmonceux. I want to use this system to plot data on the 90 nearest stars. I need, first of all, some axes of luminosity and temperature, still in the way that Hertzsprung and Russell did it, with low temperatures on the right, increasing to high temperatures on the left. And now the stars. Well, immediately we see a pattern. In fact, this is the plot that you've seen already in the text, except there it was called a colour luminosity diagram. Astronomers would call this a Hertzsprung-Russell diagram, or more likely just an HR diagram. Well, some of the stars on that plot are familiar ones. Our Sun at just under 6,000 degrees, the Sun's nearest neighbour, Alpha Centauri, and Sirius, the star which appears brightest in the night sky. And less familiar, but an interesting star, Barnard's star, which is very close to us, but it's cool, and so rather dim and difficult to see. Well, all these stars cluster around a line which is called nowadays the main sequence line. These are main sequence stars. And at first sight it seems rather obvious that they should lie in this way. These are the low luminosity stars, for instance, but they're the low temperature ones, so that seems natural. And up here, the high luminosity, well, that seems to go with a high temperature. But that's only true if all these stars are the same size. Let's ask another question. Why don't we see stars which are cool, but so large that they have a high luminosity? There are no stars there. And conversely, why are there, well, very few stars anyway, which have a low luminosity, although they're fairly high temperature, simply because they're small? Put in that way, this correlation doesn't seem so obvious at all. So we must ask the question, what feature of the stars leads to this correlation, this pattern on the plot?
Well, let me see if I can answer that question by showing you an analogy. Earlier this week, I went round all the members of the 271 course team and persuaded them, not without some difficulty, to divulge their height and their weight. And I plotted these two variables against each other on a graph. And these points represent the different people. And I think you'd agree that, as with the stars, there appears to be some sort of correlation. Now, I call it a correlation because there's a statistical scatter of the points around this line. It doesn't mean that if you have this height, you must have this weight. This line simply represents Mr. Average. Now, the reason for this correlation is pretty obvious. It's because we're all members of the same family. We all have much the same internal structure.
Could the same sort of thing be true for these stars? Well, yes, there's a strong belief nowadays that the reason for the pattern on this plot is that all these stars have much the same structure and indeed much the same composition. But that raises another question. What determines the position of a star along this line? Well, if they all have the same structure, there's really only one thing left, the mass. Well, some stars have a well-measured mass, so let me add some of those values, and it's clear what's happening. The low-mass stars are at this end of the pattern, and the high-mass stars are up at this end. So that's a new feature of the pattern, and there must be a reason for that.
Well, we believe there is a reason, and we feel the answers to be found here, in places such as this, the Great Nebula in Orion. Because you see, it's here that we believe stars are being born. You see, the whole of interstellar space is permeated with dust and gas, mainly atoms of hydrogen and helium. But every so often, we get, quite by chance, a concentration of gas in a particular area. If the density is high enough, the gravitational forces between the atoms will tend to pull the material together to form a dense cloud. Within this cloud, local density fluctuations can cause the formation of a number of smaller gas pockets, each of which will continue to collapse under the influence of its local gravitational forces to form the beginnings of a star. But as gravity pulls the material in this would-be star towards the center of the concentration, the atoms speed up, becoming more and more energetic. And this has the effect of increasing the temperature at the center of the condensing mass. As the temperature increases, the gas begins to exert an outward pressure which tries to resist the gravitational contraction. Also at this stage, some of the heat energy that is generated escapes from the surface of the newly formed star to be lost as radiation. Even so, as the core continues to collapse, its temperature continues to rise until eventually it is high enough to start thermonuclear fusion reactions between the hydrogen nuclei in the core. This release of extra energy results in an increase in outward pressure at the centre of the new star that serves to balance the inward gravitational contraction. The star has now stabilised into its position on the main sequence. But the position at which the balance occurs is going to depend on the initial mass of gas under contraction. The bigger the mass, the greater the pressure needed to support it. And in order to produce a great pressure, we need a high temperature. That's why massive stars are hot stars. But hot stars are also going to make the nuclear reactions go faster. And that means that the rate of energy generation is going to be greater. So hot stars are going to be massive stars. They're also going to be very luminous stars.
Well, the story is beginning to look quite tidy and plausible. But remember that so far we've only looked at the 90 nearest stars, and it so happens that rather few of those are bright enough to be easily seen. What happens if I add in the 100 brightest stars? Well now, some of them do still lie close to a main sequence line. Up here, the line extends further now. But there are all these stars. The simplicity of the pattern is lost. We do now have stars which are cool, but very large, so that they have a high luminosity. In fact, one of them is Betelgeuse, the very bright star in Orion, which had a reddish tinge to it, just because of its low temperature. There's Rigel, which is also in Orion, and a pole star, which is in fact a variable star. But now, what's happened? Well, we believe so strongly that these main sequence stars all have the same structure that we have to conclude that these stars up here have a different structure. In fact, we might even guess that what happens is that stars evolve away from this main sequence up into this region. But that would only be a guess. The only way really to find out about the stages in the evolution of a star is to make a long calculation involving all the nuclear reactions which are going on inside the star and which govern its internal temperature and its pressure. It's a long and very complicated calculation, but we do now believe that we have a good idea of how those stages follow on one from another. Let's look at some stages in the evolution of a star with a mass about the same mass as our Sun. Our Sun's been powered for the last 4,500 million years by fusion reactions taking place in the hot core of the star, in which hydrogen is converted into helium. We think these reactions will probably continue for about another 4,500 million years until the hydrogen in the core is used up and the fusion reactions stop. At that stage, the balance of forces is lost. The core begins to collapse again under the gravitational forces, and as it does so, it heats up. That causes fusion reactions to start in a shell of hydrogen around the core. The core's continuing collapse pushes the temperature up, and the hydrogen in the shell reacts much more fiercely. This increased energy finds its way into the star's outer regions, causing them to expand. The expansion cools the star's surface, turning it red. At the same time, the ever-increasing energy output makes the star more and more luminous. In terms of the HR diagram, the star has moved away from the main sequence to a lower temperature but a higher luminosity. We say that the star has become a red giant. Betelgeuse in Orion is such a star. So, at this stage, the star's core is a slowly contracting but non-reacting ball of helium with a shell of fiercely reacting hydrogen around it. When the core temperature becomes high enough, the helium starts to undergo fusion, being converted into carbon. And with both reactions going on, the star's structure becomes very complicated and the star may become unstable. Such a star is called a variable star. One possibility is that its light output may be periodic. In In fact, this is the region on the HR diagram where the Cepheid variables, like our pole star, are found. The helium reactions in the core can only continue for so long. Eventually, all this helium will be converted into carbon. Again, the core will contract due to gravity and heat up. And again, the shells, now of helium and hydrogen, will react more furiously, once more causing the outer atmosphere to expand. This time, though, the whole atmosphere may be blown off, leaving a spectacular object such as the Ring Nebula, seen here through the 200-inch Palomar telescope. Left behind in the center is the core of the star. It's very hot, but because it's so small, it's not very bright. In terms of the HR diagram, the core appears here as a white dwarf whose only future is to cool down and, as a black dwarf, disappear from view.
But the death of very massive stars is really rather spectacular. If the mass is greater than, say, 6 times the Sun's mass, then the gravitational collapse can be sufficient to start fusion reactions in the carbon core. And the fusion reactions will produce things like magnesium and oxygen. In fact, the process will continue until we get to iron. Now, at iron, the fusion stops, and it stops because fusion with elements heavier than iron no longer gives out energy, it absorbs energy. But of course, once the fusion stops, then the gravitational collapse takes over again. But now the collapse is so rapid and so catastrophic that nuclei literally bounce off each other and fly out into space. This is the supernova explosion, and the temperatures can be so high that very heavy elements can be produced, such as uranium. Now you might ask, what happens to all that nuclear debris? Well, it's thrown back into outer space, there to mingle with the hydrogen and helium to form dust, from which new stars can be born. So if you've ever wondered where all the heavy elements on our Earth come from, the carbon that makes up our genetic material, or the iron that fuels our industries, or the gold that we value so highly, then here's the answer. It was synthesized in countless supernova explosions dating back to the very earliest years of the galaxy. We owe our very existence to events that took place billions of years ago in stars that were born and died long before our solar system came into being.